Hi there, this is Dr. Hisham Saeed. In this video, we'll see an example of 3D concurrent system equilibrium. So the 3D concurrent system we have here is a shear log derrick. So it's kind of a system that's used to haul and hoist, lift heavy things. And like pier here, we have a load of fish. The weight of it, or the mass of it, you have to be careful. The mass of it is 200 kilograms. We're given the dimensions of the system. You can see it has kind of a triangle frame, A, B, C, and there is like a cable going from D to B to the load 200 kilograms. And the question here asks for two things. First, the compressive force inside each of the legs here of that frame A, B, and CB, and also the tension force in the cable DB, which is the same as the tension from the cable from B to the fishnet. So we have here. The first thing we need to do is to draw the free body diagram of the point. And by looking here at the end of the course, you will know what do we mean more by concurrent system, because you will see non-concurrent systems. But you can see here all the forces are going through one point, which is B. So if I draw the free body diagram, the two members A, B, and BC, they meet at the single point of B, and also the tension or the cable go through B, so whatever tension force in it also goes through B. So if I visualize more the forces, draw the forces on B, B is a concurrent system now. The weight of the load is W, and I'm showing everything here as vector. And even writing it in vector notation, so FAB as a vector is equal to FAB magnitude times lambda AB, which is the unit vector that describes the direction of AB. And the same for FBD, FCB, and even the weight force, W. Now, the problem asks for FAB magnitude, FBD magnitude, and FCB magnitude. What we're given is the magnitude of the load, which is W magnitude value, which is equal to mg. So now differentiating between really now the load and the mass. So the mass times the gravity will give us the load here of 1962 newtons. So to find now FAB, FBD, and FCB magnitudes, I need to deal with equilibrium in a 3D setting. And to do that, I have to find first the unit vectors of these forces. So this is kind of the first step of the exercise, is to find the unit vectors of the forces using the geometry. So we're not dealing now with equilibrium forces yet, but we're setting up the problem for the equilibrium analysis. So the unit vectors from the previous video, we learned that it's equal to the position vector of any point, 2 points on that direction line, divided by the magnitude of the position, this position vector. So lambda AB, the unit vector AB, is equal to the position vector AB divided by the length AB. And the same for the other unit vectors. To help us with the calculations here, I advise writing the coordinates, because the position vector between 2 points is the difference between the position vector of the ending point minus the starting point. So for example here, position vector AB is equal to position vector of B minus position vector of A, or in other words, it's the coordinates of B minus A. So if I look at the coordinates of B is 0, 4, 4, and the coordinates of A is 2, 0, 0, so it will be equal to 0, minus 2, 4 minus 0, 4 minus 0, in XYZ directions, or IJK. If I take the square root of these components, I will find out that the length here is 6 meters. And then the unit vector will be dividing the vector AB, the position vector AB, over the magnitude we have here. Do the same for BD, so RBD, and then figure out the magnitude, 10.4 meters. Do the division here, that will give us the unit vector. If you look here, BD, which is the cable, is in the plane of Y and Z, so there is no change in the X direction. So this is why I don't have I component here. RCB, doing the same process, getting the length, which you'll find that because it's kind of symmetrical here, the system is symmetrical around the YZ plane. So AB will have the same length as CB, so 6 meters. But the unit vector, you will find it's very similar to AB. So the unit vector of CB is similar to AB, except that the direction and the I direction, the sign for it is flipped. And if you look at the diagram, AB is kind of going toward the YZ plane from the positive X coordinate, or the positive x-axis. On the other hand, CB is going towards the YZ plane from the negative side of the x-axis. And they meet both at point B. So make sense of the values you calculate, try to visualize it on the figure you have, and make sure that it makes sense. Validate your calculations at different points of the solution. So now I can summarize that the force vectors would equal to now the magnitude, the unknown magnitudes of all these forces, AB, BD, and CB, times the unit vectors I just calculated in the step before. The easy one to calculate or to represent as a vector, force vector, is the weight, because it goes vertically downwards, so the direction is basically the unit vector for W is -1 K. I don't have to calculate that, it's just the direction is in basically the Z direction, -1. So now I set up the problem for equilibrium. I have all the forces in vector notation. The next step is just putting the equilibrium equation. I have it as a general equation, is a vector equation, but I can break it down into the sum of the force components in the X, and the Y, and the Z. So if you imagine this is kind of a matrix, all the vector notations here for all the forces I can put in a matrix. So just or a table, if you think. So here I'm just adding vertically here. So I'm adding the X components, Y components, and Z components, or I, J, K. If you organize the solution, actually it will help a lot in reducing the potential for mistakes. So Fx is equal to -1/3 the magnitude of FAB plus 0 plus 1/3 of FCB plus 0. So this is the first equation. It's in two unknowns, I can't solve it right away. If I do the same for the other two component equations, Y and Z components, there is no single equation that's in terms of one unknown. So I have to solve all these equations concurrently. So you can do that on your own, have fun with that. But you'll find here, this is the answer. FEB is equal to 2.52 kilonewton. So you will find when you calculate it is equal to 2520 Newton, because pay attention here, W is in terms of Newton, but it's a different representation. I can represent instead of Newton just kilonewton. So just when you calculate, it's not a mistake, it's 2.52 kilonewton for FAB, which is the same as 2520 Newton. Now, before I conclude here, just again validate the answer. The system is symmetrical around the YZ plane. So from symmetry, I expect the forces in AB and CB to be equal. I didn't set them equal force in my free body diagram. I didn't say F1, FAB, and FCB are equal. I could use maybe FB as for both of them. I pretended that I don't know they are equal, and I went through the problem, got the answer, and now I can validate it by saying I expect them to be equal, and they are equal. So I always, when I do checks, I draw happy faces after that. So sometimes it's good to leave some of the information you know about the problem that can be helpful in solving the problem. Keep it as a card to validate and check the answer. So this is a problem to analyze 3D equilibrium, but not for a general statics problem. It's for a concurrent system. You can get a flavor of how long will be the analysis of equilibrium for non-concurrent system. Anything non means bad news, right? So just a heads up, things will be more like the problems will be a little lengthy in 3D when we deal with non-concurrent, when we have to account for equilibrium of moments. So heads up for that, but enjoy 3D equilibrium here and all the vector notations we're dealing with here. Hopefully that example was helpful, useful for you, and I'll see you in other future videos. Take care of yourself and those around you.